Hi, ECS 36B student. This is my first lecture to talk about object-oriented paradigm. You might have heard about several terms that started with the prefix object-oriented. For example, object-oriented analysis and modeling, object-oriented design, object-oriented programming, or object-oriented programming language or object-oriented language construct. So there are so many things about object-oriented that's being developed for the past maybe 40, 50 years mostly in the software system or software engineering area or programming language. It's a bit confusing, but I want to first talk about there's two sides about this object-oriented paradigm. So one of the earliest object-oriented programming language is called Smalltalk. This short paragraph I actually quoted from the Wikipedia for the programming language Smalltalk. I'll just read it to you. Smalltalk is an object-oriented, dynamically typed, reflective programming language. Smalltalk was created as the language underpinning the new world of computing exemplified by human-computer symbiosis. So it's interesting. I will talk more about what do I mean by dynamically typed, what do I mean by reflected programming language. You will either learn from ECS 36B or when you take ECS 140 programming language, you will learn a lot more about the programming language perspective about systems such as Smalltalk. But there's also one thing that I highlighted here is human-computer symbiosis. It's interesting that the reason that this language was created is because we think that it's important for us to capture the interaction in a more systematic way between human and a computer. And that's actually what we're doing even today. We are using social media system to interacting with each other about our information. We're developing machine learning, artificial intelligence, and provide natural language interface for us to interact between a cobot and a real human. And so there are so many examples that when we want to have computing influence our world, that we always think about this term, human-computer symbiosis. And this was motivated by this need, and we developed this object-oriented language. So I mentioned there are two sides of OO. Now I need to be a little bit specific. In fact, this is the primary objective of my lecture, for my first lecture about object-oriented paradigm. There are two sides why we need object-oriented. There's one side which most people aware of is object-oriented paradigm really help software development. This is what we call spaghetti code. Okay, so you can look at this slide on the left that people write the code. This is a program segment under a language called Fortran. And the thing is that the control flow of the programming is very complicated. It jumps from one point to the other point. And this may be okay for 30 lines of code or even 300 lines of code. But when you move on to a large system, for example, a typical Linux operating system, probably at least 2 million lines of code in the kernel. And if you go to any kind of Windows-based operating system, it's basically about I would say anywhere from 50 million to 100 million lines of code. So when we're dealing with a really large program, a large system, it's really hard for us to look at this very complicated control flow. And because of that, it's really hard for us to reuse piece of code as well, because software development is very expensive. And the thing is that I would like to use the code that developed by others, but if the structure of the code looks like the code in the left, then I probably cannot reuse it. I probably have to redevelop everything myself. At one point of time, I heard the telecommunication carrier, their system is about 2 billion lines of code. And therefore, a huge chunk of their resources just worry about how to maintain that piece of code so they can operational and to find out what kind of bug they have and try to make sure that the undesirable situation will not taking place. And then we talk about extensibility. When we have a piece of code, we realize that we need to have a new functionality. We need to have a new way of doing certain things. And this piece of code I'm showing you on the left with this kind of structure, it's just so hard for us to make it extendable. Oh, by the way, this is a Fortran. In ECF 36A, you learn programming language like a C. By the way, C is a lot worse mainly because that C has this concept called pointer, and the pointer is equivalent to address, and pointer and address equivalent to what we call references as well. And because of this very complicated structure, and make us really, really hard to develop any large program and to be reusable, to be easily debuggable, and also it's very hard for us to extend from what we already have to the next level. So I just want to give you an example how bad the situation is in this picture. I have no intention to discourage you in terms of looking at all this complicated, challenging code segment. By the way, later this quarter, we will look at some of that because this is something which you learn from ECF 36A, and unfortunately from C to C++, and some of that will be carried into the C++ world as well. But just want to show you that how complicated things could be. In ECF 36A, you learn the concept about function call in C. And function call in C could be three different paradigms. One is call by value, which is by design that the C language, every function call is what we call by value. Well, unfortunately, they also have these things called pointer, and therefore by this language was designed to do call by value, and now is so convenient, you can also implement call by reference and call by address. And this language, by the way, also support the other concept called call by name. And by the way, call by value by itself is not so bad because you realize this is a value and then you process that value. However, mixing call by value, call by reference, and call by name together in a single programming language, in a single system, make things really, really complicated for us to understand. And the example I provided here just show you how different ways that you can actually use variable and pointer interchangeably, and also casting here and there, and then adding some arithmetic operation. And they actually sometimes they mean the same thing, but sometimes they mean very differently. And the syntax of the language and the semantic binding is fairly complicated. So what initially, that one side of the object-oriented paradigm is really trying to do a better software development, given that we have this very complicated control flow. And which means that we actually believe that OO has been that our solution. And in fact, today, that's why language like Java or C++, they're dominating our development of software system because they actually provide this paradigm. And therefore, we know that why OO is important. When I say OO, I really mean object-oriented. You probably will hear me say OO a lot this quarter, but OO really is just the abbreviation for object-oriented. It's our hope that because of the object-oriented paradigm, that we can actually develop software with very high quality, with assurance, and also we can develop in large quantity. Not to mention that we can reuse a lot of code, we can do a lot of extensibility easily. That's something which we will cover this quarter. Okay, that's one side of object-oriented. But the other side of object-oriented, which I think that is equally important and sometimes maybe even more important, because the complexity of the problem we need to deal with itself needs object-oriented. Okay, in fact, the reason I want to bring this to is that better software development talk about how you can develop a programming language convention or skill in order to implement something you already know. But the problem is that sometimes the problem is so complicated, you don't even know what it is. And then you don't know what to start. And therefore, whatever object-oriented modeling you're doing is really not solving the real problem. So this is lead to the issue of the complexity of the problem itself. I gave an example here on the slide, which shows that, oh, wait a minute, this is, by the way, this is a flowchart. It's representing how each of the step programming is leading the control flow to process the data from the beginning to the end. And this is not the most complicated. This is way simpler than a large complex system, such as operating system. And the thing is that, but this is already way complicated for us to understand. And the thing is that but typically in the real world, I'm not going to give you this flow chart. I'm going to give you a description about the system I want you to resolve. I want you to challenge. I want you to break it down. And the thing is that how do you even think about this problem itself when the problem is so big? For example, we want to solve a coronavirus situation today. That's a huge problem. I want to solve climate change issue. That's a huge issue. I want to solve all the economics internationally, how they are related, impact each other when there is some political event might happen. That's a very complicated problem. And those problems, how you're going to apply any modeling technology to understand that. Now, object-oriented might actually provide a solution for that. So what we really believe to deal with this kind of complicated real-world problem, we have to slowly shift our thinking. So traditionally, programming, we're essentially control flow driven. Control flow driven, we're thinking about, what is each of the step I need to do? The reason control flow driven is important because this paradigm is closest to the computer architecture. If you think about computer architecture is essentially a program counter in the CPU decide what will be the next instruction I need to execute. So if you think about that, the design about the computing paradigm is heavily driven by this computer architecture is followed by the paradigm of control flow. But however, control flow might not be sufficient for us to mapping the real world problem into this control flow. And the control flow will explosively grow when we deal with more and more complicated problems. And therefore, we move from the control flow driven into data driven. We look at, okay, what data is relevant to this control flow, or what data is relevant in this complicated problem. And then we need to focus on the data, and then we can start to map the control flow around this data. So this is called data driven. We focus on the data being manipulated. But then people will ask you, well, in climate change, what kind of data I need to worry about? Is that the level of carbon dioxide level or temperature for the past 2 million years, or the air pollution or industry, or some kind of energy footprint that you have? We have lots of data that potentially tedious, low level that we need to deal with. So from control flow to data driven is already a big step. We're actually focused on the right thing, but the data could be really, really complicated for us to even understand what are the data relevant. And therefore, we move from data driven to what we call data abstraction driven. So we want to provide a abstractive way of describing the data. If the data is irrelevant, the details are irrelevant, then basically we try to hide it. We try to look at all the data in our model that's critically related to the problem we like to solve. So this is called data abstraction driven. So I use a sentence here, try to tell you that in object-oriented modeling or object-oriented paradigm, when you want to solve a real problem, that what you really want to do is you want to modeling the data naturally. Naturally means that it's not something you artificially create or design, but try to model the data closest to the truth, to the reality of the object or the relationship that representing by the data. And that's actually very important, because when I'm doing that, I'm actually solving a real problem. I'm trying to pushing that to the natural representation of that data. And because of that, if you can do this modeling, you're on the right track to tackling the complicated problem. So here is the two sides. So one side, we want to have a better software engineering, better software development. That's from the bottom. We want to have a right tool to grow the development, to speed up, to improve, enhance the process, to try to implement a large system from the software development perspective. But on the other hand, we also need to think about, well, how do I really model the problem correctly, and such that I will be able to even start to think about software development. And these two, they put together is basically what I call, we need to decide what is the level of data abstraction. Because if you have the right data abstraction, you represent the real problem closest to the real problem. But then once you have that abstraction, then you can actually to do a better software development based on that abstraction. So this is a common ground for us to really build and solve the real problem. And that is the number one message I want to push on you, is that not only you start to learn about how to do better software development using object-oriented technology, such as object-oriented programming language, but also you think about, well, how do you think object-oriented way? This is what I call object-oriented thinking when you want to solve a big problem. By the way, there is a difference. I mean, this solving the real problem. Remember, well, on the slide, I didn't say solve a real problem. I solve real problems, plural. The reason is that the problem will keep coming. Today, we might solve a problem about coronavirus. 2 years from today, we're dealing with another pandemic situation, and maybe it's not virus, and maybe the environment is totally different, but somehow we learn, we have some experience from this coronavirus situation we learned today. And the thing is that if you think about object-oriented modeling, I'm actually doing object-oriented modeling for this coronavirus situation. I want to model the best I can and such that I know what's the concept of patient, what's the concept of a health system, what's the concept of a world economics. If I can actually model this naturally to this, and not only I solve this problem today, but those things that we did today can be extended to solve the problem for the future as well. So that is the important thing. We always have to remember those two things in mind. The complexity of the problem itself, and how do we actually solve the problem once we know what is the problem itself. Okay. So I give you some example. This is a Facebook page for my, okay, I just realized this is for ECF 30 a while ago that we have a Facebook page. Basically, a lot of students, just like what we have today under ECF 36B, that we have a Facebook group that we interact with each other. And the thing is that if you look at the Facebook, what they provide is a lot of object-oriented. By the way, if you think about a product or service like a social media assistant, it's essentially trying to model human being as a data abstraction, and also model how this data abstraction are going to exchange, communicating with each other. So that's all about object-oriented. So this view is talk about a very popular data abstraction about all of us. I mean, by the way, if you understand how the current social media assistant is modeling in object-oriented way, you know that you can see that how naturally they actually map the true you, that when you think about is a digital footprint in Facebook and your true self, how similar between that digital representation and yourself, and what kind of difference there. And that will tell you how successful this object-oriented modeling, this particular platform has done for each one of us. Okay, so this is from the user perspective. This is a object-oriented view. But I want to show you another view. When you look at the source code of your browser, if you use any web browser, you browse through this page, then you look at a different view about what's going on in the information. And that's the JSON view, the object-oriented view about what's going on. So the one you have, which is related to your homework assignment number 1, this is a JSON JavaScript object notation. This is a JSON representation of the same object you actually see in the previous picture. Looks very different, but to be honest with you, they represent exactly the same information. They not only represent exactly the same information, they represent exactly the same modeling. So one is more user-friendly, one is for regular user, and guess what this is for? This is for software developer. So that's why when we go back to the slides I mentioned earlier, that this is a two-side about object-oriented. If you do the modeling correctly, you not only help to solve the real problem, but also you actually provide a better software development environment as well. Okay. So now I'm going to very quickly to talk about the object-oriented principle. There are multiple principles, but this quarter I'm going to focus on this four. Data abstraction, polymorphism, inheritance, and encapsulation. So I already covered a lot about data abstraction up to this point. It basically say, well, what is the data really trying to represent? Whether this data represent a person, or this data represent a book, or this data represent a communication between a person and a robot. So how do we abstractively describe the reality of data or object? And that's the goal of data abstraction. So instead of us to worry about the detail about that reality, that I have an abstraction for me to handle this concept more efficiently. That's a very important principle, data abstraction. The other one is called polymorphism. Polymorphism means that there's a same object, but they might behave differently when their attribute or their classification are somewhat different. So, for example, if we have a class called person, we might have two types of persons. One type of person is introvert, and another type of person is extrovert. So we can have two subclasses, and you can imagine when you approach this two different kind of person, their reaction and their behavior will be very different. So this is trying to solve the real world problem because we're actually dealing with a lot of human subject interaction, but that abstraction is also useful for us to develop a system from the software development perspective to provide a detailed difference between different behavior. So in some sense, polymorphism is software engineering trying to provide a differences in the behavioral perspective about an object, but it also is natural, psychological, as it touches the object's different perspective. Inheritance is talk about relationship between one class of object to the other class. Inheritance is very important. It describes similarity. It describes where we're coming from. On the other hand, inheritance also helps in software development because I don't need to redevelop the whole thing. I can just inherit from my ancestor about the same property or the same software module. So inheritance, in a lot of sense, it helps in terms of reusability as well as try to provide some extensibility as well, because when you evolve from the previous generation to the next generation through inheritance, there's a new functionality, there's a new perspective need to be added as well. Encapsulation is another one that's very important for object-oriented principle. Encapsulation is trying to help us to neglect those details that is irrelevant to what we're worried about. For example, I assessing a particular person for a particular task A. Exactly how this person accomplished task A might not be relevant to my application when I want to interact with this person. So in some sense, their internal thinking, internal process, either as a person or as an object, has been encapsulated in such that I really don't need to access. And I don't have the right to access. In fact, encapsulation is not only talk about how to neglect the detail, but also sometimes try to encapsulate to protect the detail. Because any object, they have something which is more private and something which is more internal, which is not only the detail is irrelevant, but also maybe the detail provides some confidentiality or integrity we try to protect. So I'm going to show you some example here using a object-oriented principle. So we start to look at this object. For example, now we talk about object, we have some kind of, we call data, attribute, and then we have some kind of interface. And this picture looks like this. This is a picture of an object. And you can see that I put a boundary about a lot of the data that within this circle. So within the circle is what I call the internal data. The data that's actually the within the abstraction of the data. Some of them is about the detail that's relevant, but some of the detail is really irrelevant. And then we provide what we call the interface, which is the three functions to allow us to access, to represent the data. So for example, encapsulation is really talk about, well, what should I show in this three function I designed here, and such that it will protect the internal data, but also provide the external useful interface for people to understand the abstraction. So now I'm going to show you your first C++ example in this class called Gradebook. I pick up one example from one of the textbook. And the Gradebook is a class. It basically tries to provide abstraction about a course like ECF 36B. And we can see here there's a first function that's actually being provided is called display message. So by the way, class Gradebook is abstraction and it has a multiple interface. And the interface means that when you want to interact with the Gradebook, that there are certain external interface for any object that's outside of the Gradebook that they will be able to see. So the first interface is implemented as a function called display message. And the display message is actually very simple. It just say welcome to the Gradebook. So it's a greeting message. So that's very public. And so this Gradebook is very user friendly. And they have this function called display the message. And now I have two other functions. I said I want to have three function. And the Gradebook basically have two other functions. One is called set, one is called get. So basically I want to have a function. Any Gradebook, I need to set what is the course name of the course. And that's why I have a set course name and also have a get course name as well. And this two function basically provide interface for you for sysadmin to set the course name or to allow the student to actually get course name. But what's interesting about this is this slide, that there is some data which is quite private. That's why in the programming language, there is a section of the attribute in C++, they call it private. So under private, that means that this particular variable called course name, you cannot allow object that outside of the Gradebook to directly access. That's why it's called private. If you want to access the course name, you have to use one of the three functions. Display message, it doesn't touch it, so it doesn't matter. But set course name and get course name, those are the functions that help you to access to that. So this is basically talks about abstraction as a Gradebook. We talk about encapsulation of the variable. It talks about also about polymorphism, that because now you have this Gradebook for ECF 36B that you design this set of functions, and maybe you can inherit from the Gradebook to some other courses which you can change the semantics, which we will show you some example later in the quarter. Another example in your homework assignment number 1, or the homework assignment number 2, in fact, you will see more of this, is a class of a user of a social media assistant. Just like homework assignment number 1, you have your name, you have your student ID, and then you have another one called user ID. And then later, homework assignment number 3, you're going to add a profile photo, which is a URL. And then you might add other information like your work experience about this user. So you can actually model a user looks like this. And when you look at this, is this a good abstraction to represent a user on Facebook, Twitter, or LinkedIn? Whether that's the right abstraction, that's something you have to think about. You have to try to do that and to determine. And the other issue that which part of the information should be private, should be protected under encapsulation. I would say at least the student ID information should be encapsulated. And your profile photo should be protected to be only showable to, say, your friends or your relatives, but not necessary to everybody. And your work experience should be shown to some of the employer who might be interested to hiring you. So you can see that this abstraction of user, mixing of this 4 principles of data abstraction, polymorphism, inheritance, and encapsulation, there is a different way of applying this 4 principle to this abstraction called user. And then this is something which I think is a very important lesson for you to learn this quarter. Okay, so I want to summarize that the primary message of this first lecture about object-oriented paradigm is really this 2 sides, the complexity and the software development. So on one hand, I want you to learn all the construct, such as I show you in the C++, how you can define which part of the object should be private, which part of the object should be public, which part of the project should be protected. On the other hand, you also need to think about how to apply this paradigm to deal with a real problem. And in computer science, usually this is the quote I like a lot. You will hear me saying this again and again, is that if you haven't written the program, you don't know what you're talking about. So in ECF 36B, if you haven't tried object-oriented thinking, and based on that thinking to finish the object-oriented programming language, you don't know what you're talking about. Okay, so I will see you tomorrow in class, and hopefully you can ask me some questions about my first lecture. Good night.